Great. So we're happy today to have Tatiana Moseeva from St. Petersburg University, who will talk about random sections of convex bodies and distribution of the volume of weighted Gaussian simplex. Please.
Well, good morning. First, I'd like to thank the organizers for giving me the opportunity to speak here. That's a great pleasure. I'm really happy to be here. Now, let's start. First, about some plan for today's talk. At first, we're going to talk about some connection between the distribution of the distance between some two random points in a convex body and the distribution of the length of the random chord of this body. First, we're going to talk about the Euclidean case, and then we switch to spherical case. After that, we'll talk a little bit about the case of an arbitrary dimension of the section, and then we'll go to talking about the distribution of the volume of weighted Gaussian simplex. First, let me introduce some notation we're going to use today. By modulo some object, we will denote the volume of the appropriate dimension. So for a segment, this would be just the length of the segment. For a d-dimensional convex body, this will be the d-dimensional volume of this body. And the modulo of the boundary of the body will be just its surface area. By bk, we will denote the k-dimensional unit ball, and kappa k and omega k stand for the volume of this unit ball and the volume of the unit sphere in k-dimensional Euclidean space. By gdk and adk, we will denote linear and affine k-dimensional Grassmannians, respectively. And they will be equipped with Haar measures, nu dk on the linear Grassmannian and mu dk on affine Grassmannian. And these measures are normalized such that the measure on the linear Grassmannian, well, it's just a probability measure. And we normalize the measure on affine Grassmannian such that the measure of all planes intersecting unit ball is equal to the volume of some unit ball in the Euclidean space of dimension d minus k. I guess that's all of the notation. Let's start talking about the random sections of convex bodies. Let's consider a convex body in d-dimensional Euclidean space. Then we can find two random variables associated with this body. First, let us choose 2 points in K uniformly and independently. Then by delta, we will denote the distance between 2 points. Delta will be the first of the random variables we are interested in. Now we can take the random chord of our body. What do I mean by random chord? We take all the lines intersecting K, and then choose one of them uniformly with respect to Haar measure on the set. By intersection of this random line with K, we will call a random chord of K, and by sigma, we will denote the length of this random chord. And our goal is to find some connection between these two random variables. First, let me say why there are reasons for this connection to exist. In 1969, Kingman showed that some identity holds. And just let's look at this and understand what's written here. The left-hand side is up to some constant, just the pth moment of the distance between two random points in a convex body. And integral in the right-hand side, again, up to some constant, is just the p plus d plus first moment of the length of the random chord. So if we formulate this in probability language, we say that the pth moment of the distance between two random points is up to some constant is equal to the p plus d plus first moment of sigma. Now recall that both our random variables are bounded. And since the moments of delta can be expressed in terms of the moment of sigma, we can conclude that the distribution of delta is defined by the distribution of sigma. And so we want to know, is there any maybe explicit formula that expresses the distribution of delta in terms of the distribution of sigma? Now let me say that in planar case, so when d is equal to 2, this problem was solved by Narina Kharanian in 2015, and she showed that there is an explicit formula that expresses the probability distribution function of delta in terms of the probability distribution function of sigma. And our goal is to generalize Kharanian's result to the case of arbitrary dimension of our space. By f delta and f sigma, we will denote the distribution functions of delta and sigma respectively. They both have some integral definition, but we won't stop at this. That's not important for today's talk. And the main result states that, again, as in planar case, there is an explicit formula that expresses the distribution function of delta in terms of the distribution function of sigma. This may look maybe a bit scary, but the main point here is if we know f sigma, we can, well, with some maybe difficulties, calculate the distribution function of delta. Now let's say that if we differentiate this equality, we can get an expression for the density of the probability distribution function of delta. And it's
Tatiana, may I stop
yeah.
you for a moment? When you say random chord, does it align that goes through the origin?
No. Yeah, that's a good question. We take affine lines. So the elements of ADK, AD1.
So it's a random line, both the position and the angle.
Yes.
Okay.
Yeah, that's a good comment. Thank you. Now, if we differentiate the equality in the last slide, we can get the explicit formula that expresses the density function of delta, again, in terms of the probability distribution function of sigma. Also, let me say that as a corollary, we can derive Kingman's formula we were talking before, and also we can derive Kharanian's result for the case of the plane. Now let me say.
Can I ask, does this simplify a lot if you just take a sphere instead of a general convex?
If I recall correctly, the distribution function of the chord length for sphere is not so difficult to calculate, because if it's less than some constant, this line just does not intersect some smaller ball, and we can calculate that. So yeah, this should not be difficult. Now let me say that main instrument in proving the main result for our Euclidean space was Blaschke-Petkantechin formula. What does Blaschke-Petkantechin formula allow us to do? Imagine that we have some non-negative measurable function of k plus 1 arguments in Rd, and we want to integrate this function over the whole Euclidean space. Then what can we do? We can first fix some k-dimensional affine space, integrate this function h multiplied by some Jacobian of this transform or this linear or this affine space, and then integrate over all affine spaces. So the Blaschke-Petkantechin formula just says that the Jacobian of this transform is some power of the volume of the convex hull of our points. It's maybe, I don't know, imagined as some generalization of polar coordinates to Rd. So it's not spherical coordinates, but we can look at it at this angle. Why am I telling you about this? It turns out that there exists a spherical analog of Blaschke-Petkantechin formula, and it actually looks quite the same. So imagine that we have some, again, non-negative measurable function on sphere of k arguments. Then to integrate this function of a sphere, we can just first fix some k-dimensional now linear space, integrate this function multiplied by some Jacobian over the intersection of this space with sphere, and then integrate over all linear spaces. And the spherical Blaschke-Petkantechin formula states that the Jacobian of this transform is again some power of the volume of the convex hull, but the difference between spherical and Euclidean cases is that in spherical case, we add the origin to the convex hull. In both of these cases, I should say that K is not greater than the dimension of our space, so that both of these convex hull will be with probability 1 k-dimensional simplexes. Now that we know that there exists a spherical analog of Blaschke-Petkantechin formula, there is a question if we could generalize our main result in Euclidean space to the spherical case. And turns out that we can do that. Now let me state the problem in this case. Let K again be a spherical convex body. By spherical convex body, I mean that it's the intersection of the unit sphere with some convex cone. And we want this cone to be closed and not to contain any lines. Then by delta, again, as in previous case, we will denote the distance between two random points, but only now we take the spherical distance. This also can be seen as the angle between two independent random lines intersecting K. And by sigma, we will denote the length of the random chord of K. We just need to tell what the random chord of K is. In this case, we will, I'm sorry, we just take the random two-dimensional linear space. Excuse me. We take a two-dimensional linear space, intersect K with it, and then we get our random chord. Again, by random two-dimensional space, I mean that we take all two-dimensional linear spaces intersecting K and choose one of them uniformly with respect to our measure on this set. And by sigma, we denote the spherical length of this intersection. Now we want to know if these two variables are somehow connected. There was no analog of Kidman formula for this case known. But since we know that Blaschke-Petkantechin formula holds in a spherical case, maybe we can find some result that is similar to our general result in this Euclidean case. And turns out that we can do it. And it was...
Sorry, just about this random space. I'm not completely sure I understand the measure by which you take a random linear space which intersects the sphere. Do you pick a random point and a random angle? Is this the way to think about it? Is this then the measure on which?
Okay, see, we have a two-dimensional linear Grassmannian. It's the set of all two planes, linear. There is Haar measure on this set, uniform to rigid motions. Then we, I forgot the word. Okay, then we look only at spaces intersecting K. There is a restriction of Haar measure on this set. And with respect to this measure, we choose uniformly one of the planes. Yeah, okay. Now, this year we obtained that again, as in Euclidean case, there is an explicit formula that expresses the density function of the spherical distance between two random points in terms of the distribution function of the length of the random chord. Let me say that I showed you that in Euclidean case, we can also write the expression for the distribution function of delta. Actually, in spherical case, we can do the same, but the expression for the distribution function of delta contains some functions like the indefinite integral of some power of a sign, which of course we can take. It can be written as some sum of some addends of powers of sines and cosines, but well, it does not look very good. But if we differentiate it and get the expression for the density of the distribution function, all these not good functions just go away, and we have actually quite a nice expression. Now let me put
how does this compare to the previous formula?
Yeah, that's actually the next slide.
Oh.
Yeah, let's just see that these formulas looked quite the same. For example, the dependence of the distribution function of sigma is just the same. We just integrate 1 minus it for some over some segment. The differences are we take not the power of our argument, but the power of the sign of this argument. We lower the power by 1. Well, because now the sphere is actually d-1 dimensional object. And some constants change a little bit. But the connection, but the dependence of the distribution function of the length of the random chord actually stays quite the same. And that's interesting, I guess. We did not know that they would be so alike.
Possibly stupid question. I don't have any intuition on this. What happens in hyperbolic geometry? I mean,
yeah, some people ask these questions. We thought that this could be generalized, or that we could find an analog of this in hyperbolic geometry, but we just didn't do it. It seems like this should not be so difficult, and we just that will just change the signs to hyperbolic signs, but I don't know if that's true. We didn't look at that.
What about the case when instead of choosing 2 points, say in your convex body, you choose 3 points, and you look at the surface, sort of the convex surface contained in this, and look at that area, say just that, and compare it with you know,
the two-dimensional section.
Exactly.
Yeah.
For higher dimensions, since you have such formulas.
I will talk about that. Actually, we couldn't find the analog result for this case, but we'll get to that. Okay. Now let me stay a bit at spherical case. Well, for some points, well, for some bodies, as for spheres as for balls in Euclidean space, in spherical case, again, it's not so difficult to calculate the distribution function of the chord length. For example, when K is a spherical cap or spherical segment of some radius, it's not difficult, again, to calculate the distribution function of the chord length, because if some two-dimensional space intersects our spherical cap by some chord length less than something, then the space just must not intersect some smaller cap, radius of which we again can calculate. Now, if we remember that the measure of all planes intersecting some spherical cap is up to some constant equal to the surface area of this cap, or well, perimeter, if that sounds better, then we can calculate the measure of all these planes and then find the distribution function of the chord length. After that, we can substitute that in our result and get the expression for the density function of the distance between 2 points in a spherical cap of some radius r. Now, let's see. If d is even, we can take this integral. This won't look very pretty. We haven't found some short formula for that. But if D is even, we can get the result you can see at this slide. I don't know what to say about that. It's not so beautiful, but the point is that when D is even, we just can't take this integral, and it looks the way you can see on the slide. Now we can switch to the, again, return to the Euclidean case and talk about the case of an arbitrary dimension of the section, which we were asked about. How can the problem be generalized to this case? Again, let K be a convex body in Euclidean space. And now, instead of intersecting it with lines, we will intersect it with some affine K planes. So K-dimensional affine planes. The analog of the chord length will be just the K-dimensional volume of the section. Now, what's the analog of the distance between two random points? Well, the distance between 2 points is just the volume of the convex hull, right? Then we can try to say the same in this problem. We can take not 2 but k+1 points, again independently and uniformly in our convex body, and consider their convex hull and denote by delta the volume of this convex hull. So the question is, are these random variables delta and sigma again somehow connected, like in previous case? Well, does there maybe exist some analog of Kingman formula if there is no analog of our result? Actually, when we switch to the larger dimension of the section, the problem really becomes more complex, and that's why. When we were dealing with random chords, all these one-dimensional sections were actually quite the same. They were all segments. And all segments are similar. They are just affine images of each other. But when we switch to the larger dimension of the section, this stops being true. All the sections are not some similar. They are, of course, not always affine images of each other. And so it becomes much more difficult to obtain any analog of the results. And actually, there is no known analog of Kingman's formula for the arbitrary convex body K. But there is an analog of Kingman's formula for some class of convex bodies. Now, you see, the problem here was that all the sections are different. But there is a class of bodies such that all the sections are actually, again, affine images of one each other. That's a class of ellipsoids. And we know that each section of an ellipsoid is an ellipsoid. So maybe there was hope that we can, the analog of Kingman's formula could be obtained for the class of ellipsoids. And actually this turned out to be true. And Friedrich Gaussian, Gusakov, and Dmitry Zaporozhets showed that there is an analog of Kingman's formula, and that the pith moment of the volume of convex hull of some points in an ellipsoid is up to some constant. I'm not going to write it here because it's, well, it's not very pretty, but it depends on the dimension of the space, dimension of the section, and the number of moment is equal to the p plus d plus first moment of the volume of random section. Now, let me say that with this knowledge, there was hope that for ellipsoids, we could get the analog of our one-dimensional result that would express the distribution function, again, of the volume of random simplex in our ellipsoid via the distribution function of the volume of the random section. But we couldn't find the explicit result and finish that. But we did find some auxiliary result, I would call it, that maybe in the future could be helpful. Let's denote by phi. Yeah.
Ask another question.
Yeah.
Can you go to the previous slide again?
Mm-hmm.
So here again, you have a relationship between the pth moment, I guess, here, and the p plus d plus 1 moment.
Yeah.
So is there something that you can say about this? Like why is there p and p plus d plus 1? For example, even if you cannot prove a formula for general convex bodies, maybe there's a relationship between the pth moment and the p plus d plus 1th moment, which some sort of maybe they're related by what is it called? In a Lipschitz way or something of that sort. Can you say something of that sort?
Well, first I can say why p and p plus d plus first. The power just is okay. Let me formulate that. We get this result just by using the Blaschke-Petkantechin formula again, and the Blaschke-Petkantechin formula gives us the desired power, and also, again, of course, it's not just a Blaschke-Petkantechin formula. Here we use again that all the sections are ellipsoids. It was quite important in the proof of this fact. So I can't say that there is any analog for an arbitrary K when the section of this body are maybe not all the same. Did I answer your question?
I was sort of seeking if there's some intuition you can give which relates the p and the p plus d plus 1 moment, but it's okay. You can proceed. I didn't want to interrupt you.
Oh, okay. Thank you. Yeah, what was I talking about? Yeah, let us denote this function pk. It's denoted by a k-dimensional unit ball. And what does it stand for? We integrate some power of the volume of a convex hull, but only of the set of points where this volume is at least something. So it's something like conditional moment, if you could say that. Then the auxiliary result states that the measure of the point such that the volume of the convex hull is at least something. So it's just 1 minus of delta of x is up to some constant equal to this integral. And what happens here? We again integrate some power of the volume of the section, again over the set of planes where this volume is at least something, but then we multiply it by function pk calculated at some point. What's the difficulties here? When k was equal to 1, the function pk was actually quite easy to calculate. And after that, we could substitute it in this integral. We'll take this integral and get the main result. But in the case of arbitrary dimension of a section, it was not successful. It may be just due to the lack of some techniques. So maybe this integral could be calculated, then substituted here, and the result could be obtained. But I don't know if this could be finished. But I hope that it can be finished, but I don't know that. Because I couldn't calculate this function. Maybe.
So it's not that you've tried irregular bodies and gotten any counterexamples. I mean, maybe yes. One would think maybe a hypercube or I don't know, a simplex, you might be able to figure out what's happening exactly, even though the sections are not all similar. They're at least, somewhat predictable, and maybe you could, find counterexamples.
Yeah, maybe, but actually we haven't tried that. So, but of course, maybe it could be done, and some counterexamples could be found, but we didn't do that actually.
What is a measure of integration in left-hand side? What is the dp? What does it measure?
No, that's just the Lebesgue measure d-dimensional. that's the integral over all set of points in our ellipsoids. And that's the Lebesgue measure. So it's just a measure of the points such that the volume of the convex hull is at least something. Well, and that's a product of Lebesgue measures. I hope I answered your question.
Yes.
Okay. Now, well, let me also say that there were reasons to believe that there exists some expression for the, maybe that there exists some connection between characteristic functions of these two random variables. Well, because there exists some connection between moments, but we also couldn't find that because this, well, there is a technique when we write some identities between some polynomials and then take the limit and then write some equalities for continuous functions. But the constant CDKP is actually so not good that we could not do that. For example, when we were living in a plane and were intersecting by lines, if we look at the Kingman's formula in this case, we can write the connection between characteristic functions because in right-hand side, we will get some derivatives of some polynomial. But in the case of arbitrary dimension of the space and of the section, we could not do it. So the question about characteristic functions is also still open. I guess this would be all about random sections of bodies, and then we'll switch to the distribution of the volume of weighted Gaussian simplex. Now, what's going on? Well, we all know that the, if X is some standard Gaussian vector in k-dimensional Euclidean space, then its length is distributed as the random variable with k degrees of freedom. That's just the definition of k-distributed random variables. Actually, there exists a quite nice generalization of this distributional identity. What's the length of random vector? It's just the volume of the convex hull of this vector and the origin. And so if we take some number of independent standard Gaussian vectors, we can say that the volume of the convex hull with origin is distributed with some constant, up to some constant, as the product of independent random variables. Each of these variables has the He distribution with some number of degrees of freedom. This actually is not so difficult to see. You just use the high time base formula for the volume of simplex, and you also use the spherical invariance of the standard Gaussian distribution. Now, it's also easy to see that if we take not just standard vectors, but we take them with some weights, so we multiply them on some positive numbers, we can find the volume of weighted simplex, the distribution of the volume of weighted simplex, and it's up to some constant again, depending on the weights, is distributed as a product of independent He distributed random variables. But what happens when we delete the origin from the convex hull? Actually, now the problem becomes more subtle because, well, just not because, the problem becomes more complex. What happens when all the weights are equal? So it's, well, unweighted Gaussian simplex. The moments of the distribution of its volume were calculated by Miles in 1971. He showed that there is such an expression for the volumes of for the moments of the volume, and then using the known moments for key distributed random variables, he concluded that such the distribution identity holds. Well, how did he do that? We know the moments of the key distributed random variables, so we can apply the method of moments and find the distribution identity. Although Miles did not prove that in any way, so he just concluded that method of moments could be used and the distributional identity could be obtained. Let's also say that in this case, the case of different weights does not follow from the unweighted case. That's because the L-dimensional volume is not affine invariant when L is smaller than the dimension of the space. So we have to think of something to solve this problem. And in the case of not, in the case of different weights, the moments of the distribution were found this year by Dmitry Zaporozhyn and random Furling, and well, they found this identity. But well, that was not an easy computation. It took several pages and some quite difficult techniques. And since the authors did not need the distributional identity, they only needed the expression for the moments, they again concluded that the distribution identity could be found via the method of moments, but they did not do that. And also they suggested that the distributional identity could be found without calculating the moments, without using the method of moments. So they concluded that the distribution identity could be found while using only some geometrical reasons. And the goal was to find this proof, to find the distribution of the volume of weighted Gaussian simplex without calculating its moments. When that was successful, and we proved that the distribution of the volume of weighted Gaussian simplex is up to some constant, depending on the weights, equal to the distribution of the product of L independent He distributed random variables, and the variable here k has the He distribution with k degrees of freedom. Now I want to tell you maybe the plan of the proof, because, well, it uses some interesting facts, as I think, and also we have time for it. Now let's start. First, for the case of the simplex of full dimension, so when the number of points is d+1, that's not very difficult. We just transfer the simplex so that it contains 0 as one of the vertices, and then we write its volume as some fraction of the volume of the parallelotope spanned by these vectors. And we know that the volume of the parallelotope can be found as the determinant of such matrix. Now look at this matrix. We can look at the columns of this matrix, but they are not independent, as you can see. Well, they all have x0, for example. But if we transpose this matrix, its columns become independent. And, well, the determinant does not change. Now, let's also say that not only the columns of this matrix are independent, they also have the same covariance matrix. This may be not so easy to see just from this picture, but that's true. And the covariance matrix looks this way. So what can we say? We have the independent Gaussian vectors with the same covariance matrix. So we can say that they are just the images of independent standard Gaussian vectors under some linear transform A. such that A(n) transposed is the covariance matrix. Now it's not so difficult to calculate the volume because we know how the volume changes under the linear transforms. And so the volume of our weighted simplex is up to some constant equal to the determinant of our linear transform, which we can calculate, and the volume of the parallelotope spanned by independent standard Gaussian vectors, which we also know we were talking about it actually in the first slide of the second part of our talk. So the volume of the parallelotope spanned by independent standard Gaussian vectors is just the product of heat distributed random variables. And so we just find the determinant of A and conclude that the volume of weighted Gaussian simplex, in case when the simplex has the full dimension, can be calculated as follows. Now, what do we do next? How do we switch to the case of the lower dimension of the simplex? Well, we have to do some quite important step. What's happening? Let us consider the affine hull of our points and then just project it so that it could contain the origin. So we just take the linear space parallel to our affine hull. And what can we say about this linear space? It turns out that this space is first distributed uniformly over the L-dimensional linear Grassmannian, and second, does not depend on the volume of the convex hull of our points. We can think of that as generalization of some property of Gaussian vectors. We know that if we take the length of the standard Gaussian vectors and divide by it, we have the point on sphere, which is distributed uniformly on this sphere and independently of the length of our Gaussian vector. And that's somehow the generalization of this fact. So the volume of the convex hull and the linear hull of these planes are independent. And the linear space is, again, distributed uniformly over all these spaces. That's, well, it's not so difficult actually to show. It's the same as showing that the standard Gaussian vector has its property, but, well, for me, it was quite unexpected. What can we do later? Let's consider the projection to the first L coordinates. And then we can say that the volume of our weighted simplex multiplied by the determinant of this projection is equal to the volume of the projection. Now, what do we see here? We have projections of standard Gaussian vectors onto some L-dimensional space. Well, we know that the projection of the standard Gaussian vector has the standard normal distribution on the space, on the space we are projecting to. And so we actually know the distribution of the right-hand side, because now we have L+1 vectors, standard Gaussian vectors in L-dimensional space. And so we know the distribution of the right-hand side, and we have the following distributional identity. Now, what do we want? We want to find some similar identity, but we change the desired variable here by the distribution we want to show it has. Now, let me be more clear. Consider independent standard Gaussian vectors, again, L vectors. Take the linear span, and we can say, again, it's similar to the previous case, that the span is distributed uniformly over all L-dimensional Grassmannian and does not depend on the volume of the convex hull of origin and our vectors. Then we can again project, and since W has the same distribution as our space WL, they are all distributed uniformly over L-dimensional Grassmannian, then we can write this identity again. But in this case, we know not only the distribution of the right-hand side, but also the distribution of the volume of the simplex in left-hand side. Here, that's a misprint. Of course, the modulus should be also here. This we also talked about in the beginning of the second part. We know the distributions of both parts. And so we have, I've written here, both distributional identities we have. And after that, we only need to, we need to prove this, that if we have these distributional identities, then the factors in left-hand side have also the same distribution. And that's actually true. So if we have some, well, positive random variables with probability 1, and we know that the variables in the right-hand side, left-hand side are independent, and we know that the right-hand side are distributed identically, and some factors in left-hand side are distributed identically, then the other factors in left-hand side also have the same distribution. After applying this lemma to our case, well, and multiplying the second identity by the constant we need to multiply it by, we get the desired result. Actually, lemma is also not so difficult. You just, well, you need to take the logarithm of both equations, and then you have the same problem, but not for the product of independent random variables, but for the sum. And when you have the sum of independent random variables, you can use the apparatus of characteristic functions and win. And so we use this not so difficult lemma and get the desired result. And I guess that would be all. Thank you.
Thank you very much, Tatiana. Are there any questions? Okay, so if not, then thanks, Tatiana, again. Thank you very much for the nice talk.
Thank you.
And to take an 11 minutes break and meet exactly at 11 for our second talk by Professor Lucius.